All right, thank you for joining me for calculus today. We're going to look at power series. I'm going to look at a couple different aspects of things, and we're also going to go back and reference a little bit about the idea of convergence along with this. A couple of things I just kind of want to hit on as we run through this is that over here on the right in the blue here, we have your basic definition of what a power series is. So you have something being raised to a power and you have some type of coefficient with it. That's what C sub n is just some coefficient. And that coefficient can change within each individual term. So again, remember we're dealing with series. So that means we're doing the sum of lots of different terms. What we're doing with this particular piece is we're kind of standardizing what that individual term needs to look like. And we're going to name this as a power series. Now, why power series? Because we're taking it to a power right there, right? Now, this should sound familiar, or at least looks decently familiar, in that we are dealing with a P series of sorts, right? So we have some type of value being raised to a power. The power here is our variable. So actually, you might be thinking, well, that means that this is actually a geometric series because we're doing some standard value here being raised to a power. So there we go. Right, so the differences, or what we're dealing with here, is the fact we have this power piece in there, which is one of the kind of the connections back to the power piece. So just keep the idea of the geometric series and the P series in the back of your head as you deal with these. Again, those should kind of be kind of your default go-to places. Now, what you're looking at here on the left is just a table that I've just stuck right there that is a fairly common series expansions for the better known series that you will deal with in C. E to the x cosine sine. You have your words, right? You have your sine, your other sine functions there. Hyperbolic sine and hyperbolic cosine there. And you also have 1 over 1 minus x and 1 over 1 plus x, and then arctangent, and then ln of 1 plus x. Now you may be wondering, why don't we just use ln of x? Well, there's some other things going on there that make ln of x more difficult to deal with than ln of 1 plus x, and we'll go to that. Now the idea here that we're dealing with a power series is that we're always centered at some value of a. Okay, so x minus a. So all these terms are going to be x minus a. You may be saying, well, where is this for the first one? Well, n is equal to 0 for that first term, so anything to the 0 power is 1. So x minus anything to the 0 power would be 1 right there. Now, the thing we want to deal with is, does this series converge? That's a big question that we want to talk about. One of the things that we were going to look at is, let's talk about e to the x for a second. This is a equal sign between e to the x and this infinite series here. And just to kind of to remind us a little bit, when you talk about e to the first power, that exact value is 2.718281, and it just keeps on going and going, right? So we can't actually write down the exact value. But when we write down this series here, we are writing down the exact value of e, okay? There's an equal sign, so this isn't an approximation, it's an exact value. But one thing we can also do is we can also approximate this. So let's just say that we do e to the first value, and we say we want to approximate that just using the first two terms. Well, that's 1 plus 1, which is 2, so e to the first power is approximately 2. Well, that's decently close. E to the first power is approximately the first three terms, right? It'd be a better approximation. So look at our expansion there. So 1 plus 1 plus 1 over 2, right? So that's 1 plus 1 plus 1 half, right? And that gives us 2.5. So now we're even more accurate than we were a second ago. Well, the next term there for the either first, the next approximation that we would do would be 1 plus 1 plus 1 half plus 1 over 3 factorial, which is 3 times 2, so that's 1/6. That gives us 2.6 repeating, which is even closer to that 2.7. When we do e to the first, and we just take this out to the fifth term, so 1 plus 1 plus 1 half plus 1/6, e, and then that one, the next term would be 1 over 4 factorial, so that's 1 over 24, right? And that'd give us 2.708, and that keeps on going actually for quite a while. we're at this point really close. We're only off by one. This would be your tens place, your hundreds place would be that second decimal place, right? So we're off by 1/100ths at this point. So we're massively close. This is another way that we can do the approximations to whatever level of accuracy we need for e, and for any of these really. And we can also do other powers. We could say e to the second power, and we want an approximation for that. So we could do the next one there. So, and we can see that 4 or 5 terms give us a pretty accurate value there. So let's just go ahead and plug that in. So it's 1 plus 2 squared over 2 plus 2 cubed over 3 factorial. And of course, that'd be 2 factorial right there too, right? And then 2 to the 4th over 4 factorial, right? And then we just keep on going depending on what level of accuracy we want. If this is the level that we're wanting to get out of it this go around, well, we can just simply type that in as we see it. And I encourage you to pause right now and do the calculations yourself and make sure that you can come up with the same value that I'm going to get here in a second. So I'm just going to go through that piece there, and 4 over 1 plus 2 squared over 2 plus the next value there would be 8 divided by 6 plus the next one, which would be 16 divided by 24, right? And you just keep going through that value. When you do that, you end up with this value being 7, right? And if you do on your calculator e to the second power, what you come up with, the exact value, e to the second, is exactly, and actually I shouldn't even write it that way, but 7.389, and that decimal keeps on going forever, because essentially what you're doing is 2.718281 blah 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 squared, and you come up with 7.389, which in this case is pretty close to 7. So that's a pretty decent approximation. We would have gotten a lot closer just simply by adding one more term on there. We probably would have gotten the 3 piece in there with that next one. Who knows? But try that out and then just kind of play around with it. So you can do this with all of them, and I encourage you to go through with all the ones that you can to sit down and just try these different values out and just see what they do when you plug them in. And then notice that these series are all starting at 0 except ln of 1 plus x. That one's actually starting off at n equal to 1. And there's a reason for that, a very good reason. And I encourage you to play around with that and see what you can come up with. Try it at equal to 0. Try it with it just being ln of x and see what happens when you have the different values going on there. So the question you might be asking is, well, how do I start it at? What would that look like? Well, you can do some movements here, right? And some of the following videos might be more helpful with this as well, but you can do some movements here, thinking about n starting at 1 for this counting process. Well, how can you offset? How can you make this fit into that still by also approximating this or making this fit in at 0? Well, what if you let x equal -1? Which means you'd make adjustments over here, which means you'd make adjustments over there, right? So you'd have to fit in there. So now you'd be talking about ln of 0, right? What happens when you plug in -1 into those values? What happens when you plug in, you do ln of 0? What would that be equal to? That creates some issues. So just kind of play around with those values and see what you come up with when you do those things. All right, take care.